Hello, good people. I'm going to do the next three examples in this order. We're going to do example 4, then example 5, then example 2. And if we have time, we'll do 6. 6, I'm not too worried about because I think once you get the first 5, the last one, since we already broke it up into two pieces and we already know the answer to one piece, the first part should be okay. So let's start with example 4 here. All right, do we have everything we need? I don't think so. Not only that, not only do I not have what I need, I have extra stuff. So a couple of things to recognize. I have the u identified, and I know what my du should equal, but I don't see a -2 anywhere. And on top of that, I see a +3, so that's even worse. So here's what we can do. Why don't we pull this 3 out like we usually do? If it's a constant, pull it out to the front. So I'm going to pull out the 3, and then that's left over, and this is still there, and this is still there. So I haven't changed it in terms of u. I'm just unmultiplying, factoring out the 3. Okay, now what do I need? I need a -2 dx. Well, I have a +1 dx. So I can multiply this by -2, and that would make it a -2 dx, and then I can replace the du. But if I do that inside of the integral, I have to balance it out by dividing by -2 on the outside, or multiplying by -1/2. I guess that would be the other way to think about it, right? If I'm multiplying by 2, then on the outside, I'm going to multiply by -1/2 or divide by -2, and then that's going to keep it balanced. So what I wrote here, the green can reduce out, and I'm left with what I started with. I haven't changed the value of the integral, but I made the integral so that now I can say on the outside, I have 3 over -2 integral. On the bottom, in the denominator, I have u. In the numerator, I have -2 times dx, which is du. So let me replace that in green, du. So here I had what I needed. I can replace it that way. I can also write this over here to the side and just say, oh, that's 1 du. Does that look like a familiar antiderivative that we can take? It was one of the 5 rules that Brian told you have to know. Stone cold, you got to know these antiderivatives right away. This antiderivative would be the natural log of the absolute value of u, except I have a constant in front, and then I plus c it. Does that make sense? And now I can revert back into the world of x's, and my true antiderivative that I'm looking for would be the natural log of the absolute value of 4 minus 2x plus c. We put the u back in, that u expression back in, and we have our antiderivative, indefinite integral. And that's it. So think about the work that we did here. There was an extra constant. I pulled it out, and then I multiplied the way I did the previous example. I multiply by what I needed in order to get my exchange perfect. So now I can exchange -2 dx, -2 dx. I can exchange it for a du, 1 du, and then I can take it from there. So we're going to practice this again because I think it might happen in the next example that we do. How about number 5 here? Example number 5. Do I have the u identified? Yes. Do I have the du identified? Yes. Do I have 3x? I don't have 3x. So what I could do, and eventually you won't need to show this step. You just do it in your head. But I want to show you what's happening. I'm pulling out this -4. When I do that, there's something left in the numerator, and that would be a 1. Because if I multiply it back in, that'll give me -4 over that quantity squared. Oh, but I need 3 dx. I don't have 3 dx, I have 1 dx. So I can multiply this by 3, but if I multiply by 3, I have to balance it out by dividing by 3. But now I have what I need. And so everything that I double underlined in green, I'm going to replace it with a du. I still have -4 thirds on the outside of the integral. And then here, remember, I replaced this with 1 du, so then I have 1 du. And then on the denominator, I should have u squared. So I'm going to give you a chance to catch up on the notes, but also writing the notes, but also think about what we just did. This constant, pulled it out. Did I have what I needed to make the du exchange? I didn't, so I multiplied by the constant that I needed. I needed a 3, so I'm going to multiply by 3. But doing that is going to change things unless I balance it out with dividing by 3 on the outside. Now I can exchange that for a du, and then 1 over u squared, because we said that 5 plus 3x was u. How do I find the antiderivative of this? Usually I have a student that says, can I take the natural log of u squared? No, you can't take the natural log of u squared. What we can do is, let me not do it in this color. What we can do is rewrite it. I don't know why I wrote that there. As u to the negative 2. And then I can use the power rule. The power rule that says add 1 to, the reverse power rule, add 1 to the exponent, divide by the new exponent. So then this is negative 4/3 times, add 1 to the exponent, divide by the new exponent. And when we do that, plus c, by the way. And when we do that, that's going to give us positive 4/3 u to the negative 1, but I'm going to make it a positive exponent by flipping it down, and I'm left with this. This would be our antiderivative in terms of u. So if I come back in terms of x, this is going to be 4 over 3 times 5x plus, or 5 plus 3x, my bad, plus c. And that's our answer. This is the antiderivative that if I differentiate it, if I take the derivative, I get back to this. It works each and every time. I promise. So, again, the process is the same. Identify the u expression, find the du exchange rate, I call it. See if you can replace the u and the du. Do you have enough information constant wise to replace both? Once you replace both, that's not the end. You still need to take the antiderivative. And then if you're doing an antiderivative, definite, indefinite integral with no numbers, limits of integration here and here, then we need to put it back in terms of x. We're going to do one more, and then we'll pause here. And we'll wait till the next to see what happens when we do have definite integrals. Okay, so here, do we have enough of everything? This is going to be my u expression, and then I need 3x squared dx. I don't have that, so I'm going to multiply by 3. But if I do that, I got to multiply this by 1/3, so I can keep it balanced. Now here, I have what I need. So this is going to turn into 1/3 integral of 1 du over the square root of u. Notice u is just the inside, so don't just write 1 over u. It's 1 over the square root of the inside, which is the square root of u. Can I take the antiderivative? Sure, I'm going to need to rewrite it, but I can take the antiderivative. By the way, let me do this in green because I've been doing it, the du in green, just so that you can see. This replaced all of this that's double underlined, because all of this that's double underlined is what du equals. So it's a clean exchange, right? I need to rewrite it here, so I'm going to rewrite it. This is not the antiderivative. 1 over the square root of u is u to the negative 1/2. And now I'm going to take the antiderivative. So the antiderivative says constant times, add 1 to the exponent, divide by the new exponent, plus c. And if I put this together, that'll be 2/3 u to the 1/2. But remember, u to the 1/2 is just the square root of u. Which means my true answer in the world of x's is 2/3. Let me do that in purple. 2/3 square root of whatever u was equal to. U was equal to this plus c. And that is the antiderivative of this complicated looking thing. We're able to do it. Again, I want you to notice we started with this complicated looking rational fractional function, but when we did use substitution, we made it look simpler. And then we were able to take the antiderivative. That's the purpose of use substitution. It's a method of taking antiderivatives by making an expression, a complicated looking expression, less complicated. Or as Brian says, by replacing the junk and making it look nicer. Those are the first 5 examples here. If you want, we can do this one real quick. It's not going to take too long because I need 3 dx. I don't have a 3, so I'm going to multiply this by 3, but then I got to balance this out with a 1/3. And now this one will become 1/3 antiderivative of sine u. And then now I do have enough information to replace this with a du. Minus the antiderivative of cosine x, which would be sine x plus c. Oh, I haven't taken the antiderivative. I need to take the antiderivative. The antiderivative of sine u would be negative cosine u. Okay, so that's 1/3 negative times negative cosine u minus sine. I've run into an issue here. I can't mix variables. Either I stay in the world of x's or I stay in the world of u's. And I made a mistake here by combining both worlds. So let me finish this off by putting the u expression back in here. And then this would be the final answer. So I'm claiming that the derivative of this is this integral part. Okay, I'm going to leave this showing. Again, we did the first 6 examples. Practicing this use substitution, we're going to get a lot more practice in class, I promise. But in the next video, I want to show you what happens when we have a definite integral. How does that change things?